Hey guys, welcome to this third video on this series on quantum coding. Today's topic is quantum entanglement, and which is a super exciting topic, and this is the magic which makes quantum computation super awesome. And today's beverage of choice is cosmic distortions. I don't know if you can see this. All right, so let's dive in. So today we will basically um, I'll give you a theory about quantum entanglement, and also we will implement it on an actual quantum computer for the first time. So I'm pretty excited about today's video. And so let's just dive in. Just give me one moment while I set things up. All right, so, ooh, just, okay, let me center this. Great. So we saw a single qubit system last time. And now let's talk about what if we have a system of two qubits. So just like before, assume you have two hydrogen atoms or two electrons or whatever they are. So you will represent state by, again, the bracket notation, ket, where the first element would be the state of the first qubit and the second element would be the state of the second qubit. So first element, first qubit, second element, second qubit. So let's look at how a state would look like. So the state, like I said, if you don't remember, please go back and check out the other videos. But then the state of a quantum qubit, or rather quantum bit, is a superposition of both the 0 and 1 state. So I have some complex number times 0 plus some complex number times 1. And the same happens for the second qubit as well. Complex number times 0 plus some complex number times 1. So the combined state of my system looks like this. So it's um, when both some complex number times when both are at ground, one is at ground, one is at ground. When, sorry, both are at ground, one is excited. This is also one is excited, and when both are excited. So just like a single qubit, which was in a superposition of two states, double qubits or two qubits can be in the superposition of states where they range from like both ground states to both excited states. So pretty simple. This is just like a product where I have multiplied the state of first times the state of second. Now, this is when entanglement comes into the picture. Again, like this is a whole topic in itself, but I just want to give you the bare minimum. So an entangled state is something that looks like this. So, my bad. So an entangled state looks like this. So you can see instead of having four, like 0, 0, 0, 1, 1, 0, 1, 1, I just have two, 0, 0, and 1, 1. And the probabilities are they're both multiplied by 1 by square root 2. So the square of both, when you add them up, adds up to 1. So this state is special. And the reason why this is special is you cannot write it as a product of two states. So here, when we multiplied, we got this combined state. But this particular state cannot be written as a product of two separate states. And that is why they're called entangled, because they're not two states that came together, but then they're like a bound state of two bits that is a separate state by itself. So this thing cannot be decomposed into state of first qubit or state of second qubit. This is a state by itself, and that is why entanglement is so special. Now, when you perform measurement, right? So let's go back. So when I performed measurement on, say, the first qubit, I would get either the state 0 or state 1, right? So measurement gives you classical states. So you either get 0 or 1. When I perform measurement on this state, I would get either 0, 0 or 1, 1 because these are the two possible states, both ground or both excited. Now, I should mention this is one possible entangled state. I could have like different possible entangled states like 0, 1 plus 1, 0. So I will just go with the simplest one. So when I perform a measurement, this state collapses to 0, 0 or 1, 1. Now, what's that telling me? That's telling me that if I measure the first qubit, I would know what the second one is for sure. Now, that is, I mean, right now that might seem very intuitive to you, but think about what it's doing. So imagine you have an entangled state. So because of this factor 1 by root 2, you could get both the states with some probability. So the probability is half. So 50% of the times you'll get this state, 50% of the times you'll get this state. Now imagine you take the first qubit to the moon and the second qubit you have on Earth, right? So if you measure the one that you have on Earth and you find it to be a 0, then you know for sure what the moon one will read when measured. So that's the crazy part. Like if you measure it and you find it to be 1, then you know for sure the moon qubit is also 1, right? So in this state, if you were in this state, you wouldn't be sure because say if you measured the first state, the one that you have to be 0, then the one on the moon could be either 0 or 1. But here, because you just have these states, you're 100% sure what the other one would be. And this is a source of great mystery, and there's tons of research done on it. Again, I'll abstract all that away, but then let me tell you, this is the secret sauce of quantum mechanics. So, quantum mechanics requires two main ingredients, or rather, quantum computation. First, a qubit can store an infinite amount of information because it has a all complex value of states. The second is quantum entanglement. And because of entanglement, you can do a lot of like interesting things like quantum teleportation and lots of fancy stuff. So again, because my entangled state when measured becomes 0, 0 or 1, 1, if I measure the first one or if I measure the second one, I would instantly know what the other one is, what's the value of the other one, no matter what distance they are separated by. So that's the crazy thing. So that is how quantum entanglement works. So now what we will do is I will tell you how to set up your first, how to set up quantum computer. Basically, we will be using IBM's public quantum computers, and then we will write our own script that creates a qubit and measures it, or rather creates an entangled qubit and measures it. So let's get on with it. Okay, so now I will first walk you through how to set up your first quantum computer, rather like how to connect to one, and then we'll take it from there. So go to this web page, quantum-computing.ibm.com, and you will have to create your own account. And creating an account is totally free. So this will basically give you access to IBM's public quantum computers and quantum servers. So after this, what you need to do is, so this is how your dashboard would look like. Then, so you will get an API token. So to use IBM's quantum computers, you first need to authenticate with their servers using this API token. So copy this token and save it in a file. So I have already done that, so I won't talk about those steps, but then just save those things in a file. So once that is done, now let us get to coding our first entanglement or entangled state and then measuring it. So, all right, so let's begin. So let me get rid of this. All right, so I am back to my Jupyter notebook, and if you haven't, please check out my last video where I go on and on about how awesome it is to use VS Code to use Jupyter notebooks or just code it in here. So let me set up my system. Okay, great. So we first begin by importing Qiskit, and we want matplotlib inline, which will help with the plots. Also, we probably need to import the IBM backend for Qiskit. Okay, so that is set. That's good. Now let's construct our simple quantum circuit, which, because we are making an entangled state, it requires 2 qubits, and then because I want to measure both of them, it requires 2 classical qubits. So now I will do some operations, which I don't want to go into the details of it, but the basic essence is that these operations generate an entangled state. Okay, so let me first tell you what's happening over here. So first, I have created a quantum circuit with 2 qubits and 2 classical bits. Then I first apply a Hadamard gate to the first qubit, and then I apply a CNOT gate. Again, the details aren't relevant, but then the point of these two operations is to generate an entangled state. And then what I do is I measure it. So this is a new way of measuring, which is different from what we did last time. So here I'm entering what. So the first entry is what qubits I want to measure, and the second entry is where do I want to store them. So which classical bits I want to store them. So measure 0 and 1 and store them in classical 0 and 1. So pretty simple. Now we can just draw a circuit out, and this is how it looks. So yes, this is all good. Yeah. So you can see here's my first quantum bit and the second quantum bit, and these are the 2 classical bits. So on the first one, I apply this Hadamard gate, and for the second one, I apply this CNOT. What it does is basically after this step, I get an entangled state. I get the same entangled state as, so basically I get this state, 0, 0 plus, oh, my bad. Yeah, sorry, my shortcuts were acting up. 0, 0 plus 1, 1 with appropriate normalization. So after this gate, I get 0, 0 plus 1, 1. Oh, I'm sorry, that went below the screen. So yeah, after this gate, I get this entangled state, 0, 0 and 1, 1. Good. So let's carry on from here. So this is, do I need to? No. Right, so let me delete this. I'm still getting used to writing IPython code in VS Code. Great, so now that we have our circuit ready, let us, let us connect to the quantum computer. So to do that, basically I will copy a piece of note and let me explain what that does. So first of all, I have saved the token that I told you about in this file, token.txt, and I need to load it in like this, and I'm supplying the override flag to be 1. Then I will, basically these steps you have to do as is. Then I load my account, and then I check for providers. So, I mean, don't think too much about it. Just think of this as just an interface commands that you just have to use as is. Oh, this is, let's see, what's wrong? Oh, right. Good. I I have connected to their um, to my account that I have created. Again, this file contains my token that I have used, that I've copied and saved in this file token.txt. So now let's get a list of quantum computers that we have access to. So I'm gonna copy a bunch of code from my notebook, and this is just pretty much taken from basically one of the examples somewhere on the Qiskit forum, and let's try it out. So great. So let's wait till it populates. Now take a moment, take a break here. Take a moment to realize that right now you have access to all of these quantum computers. These are not simulators, these are actual legit quantum computers. So whatever you would be doing, there would be some quantum mechanics experiment going on whenever you run your circuit. Some quantum circuit on one of these quantum computers runs. So your circuit will run on one of these quantum computers. So you right now have access to all these computers, and you can see whether there's a queue, there's how many qubits they use. So for example, Athens has a queue of 8 and it's using 5 qubits. So I will probably go with that because the queue is low. So let me first select that. So just like last time, we selected the simulator. This time we will select our backend to be one of this. So we select IBM Q Athens. And the goal is, so what is my job? My job is to execute the circuit that I made. Where? And the backend. That means that quantum computer in Athens. And how many times do I want to repeat it? 500 times, just because I can. So that sets up my job. Now to get to run my job, what I need to do is just just call this function job.result, and that will run my job. But okay, so let me just do that first. So let's execute our gig. So this is an async process because you see it's being executed because right now we are queued up. As you saw, like we are 8th in line. You can write a better version of this code by where it tells you what's your current queue standing and shows you, hey, your job will be executed and after so many people and so on. But I've written a pretty basic code, so we'll just wait for it to be uh, done. So at this point, I'll just pause the video and resume once it's done. Okay, now that it has successfully completed, let us get the final results. It took longer than I hoped. So result dot what am I doing? Get counts circuit. Oh, it's results. Yes. Huh. Right. So let's see. What do these? So these numbers actually came from a quantum computer. So let's see what they mean. Now remember, the entangled state was 0, 0 plus 1, 1. Excuse me. So when the state collapses, it's either 0, 0 or 1, 1. So here you can see you get 0, 0 241 times, you get 1, 1 241 times. But then you get these other states 0, 1 and 1, 0 some small number of times. That's because actual quantum systems currently are very susceptible to noise. Even like very minor variations in temperature adds in a bit of noise. So that's why we had to repeat the experiment 500 times to be sure. So let's try it again. And this time, I just like while this code was running, I found a piece of code that would help monitor my job status. So let me, right. So from here, let me import job monitor, and this will basically monitor the status of my job. So let's try this again. It's telling me my job is queued for. So, but you see the point. So we first created an entangled state, and now we are measuring both the qubits of the entangled state. So the entangled state that we created is basically just this and so both occur with equal probability. So whenever we measure, so after measurements, it should be either this or this. Right, so and we store this first value in the first classical bit or second value in the second classical bit, and same for this. So we should get 0, 0 or 1, 1. And that's why the probabilities for 0, 0 or the counts for 0, 0 and 1, 1 were the highest. The rest are just noise. And we will verify this again. But the crazy thing is that we are actually creating an entangled state, and then we actually measured it on an actual quantum computer sitting at home. So I mean, it just blows my mind where technology is right now. So right now I glossed over like what these gates do, but then that's the topic for the next lecture where I'll talk about what these gates do. And these gates are the basic operations. So in a regular computer or in like, the circuits that we have, and, not, or are the basic operations. In a quantum circuit, there are these operations, Hadamard. There's versions of and, not, whatnot, but these are the basic building blocks of quantum circuits. So let's see, our job is still at number 4. Um, yep, I am gonna pause the video and resume when it's done. Okay, I'm back. So now here it says job has successfully run. Great, and now let's check the results and see what we got. Print that out. And again, you can see 0, 0, 249 times, 1, 1, 232 times, and rest noise. So we've actually created an entangled state and measured it on an actual quantum computer. So I think I'll wrap up this video here. I hope you guys enjoyed it. Again, so I know the theory of quantum computation, but this is the first time I'm also doing, and I'm doing it on. I'm actually coding it up. So so I am learning as I go. So I hope you enjoyed this video, and please like and subscribe if you liked it, of course. Thank you so much. See you next time.